This is the second video on two-body central force problems. In the first video, we started by looking at this problem here of two particles or bodies or planets, electrons, what have you, that are interacting through a central conservative force. If the force is central and conservative, we know that it doesn't depend on direction. So the potential associated with it will have this form. It will only depend on the distance between the two. Its magnitude will only depend on the distance between the two particles, and therefore the potential will only depend on that distance. We showed in the last video that under these circumstances, the center of mass frame, that is the frame where this expression here, the center of mass position, is 0, that frame is inertial. And in that frame, we can take the Lagrangian and write it on this form. 1/2 mu r dot squared minus u of r, where r again is the relative position vectors, the vector from m2 to m1. And mu is the reduced mass here. So in the center of mass frame, we have this Lagrangian. Okay, so what we've done now is we've essentially taken this two-body problem with 6 independent variables, and by shunting aside the center of mass movement, which will just be constant momentum, total momentum of the system is constant, we have reduced it to a single particle problem, or an effective single particle problem in any case. What we're going to do now is reduce the complexity of this problem further, and to that end we're going to look at the angular momentum. So the angular momentum L of the system, and we know from the definition of angular momentum that's going to be R1 cross P1. That's for the first particle, M1 here, its position of momentum crossed, and then we add in the angular momentum for the second particle. And we can just rewrite this. Now, to make further progress, we're going to change variables to capital R and little r. Capital R, of course, is already 0, so that will just disappear. We're going to change from R1 and R2 to little r. We saw in the last video that R1 and R2 are given by the following formulas. That where capital M is just the sum of the two masses. Now this is equal to, in the center of mass frame, where capital R is 0, we just have this. So we can just substitute these two expressions in here, and we'll get the angular momentum in terms of little r. And discover here I put the dot in the wrong place in all these expressions. So what we can see here is that the angular momentum in this system also behaves in a sense as the angular momentum of a single particle with mass mu. So that's kind of interesting. We had an well, not so strange perhaps, because what we had here is a Lagrangian that is a Lagrangian of a single particle in some potential. Although the variable r here is actually the vector between two particles, but it's an effective single particle Lagrangian, and it stands to reason then to perhaps that the angular momentum of the system is also the angular momentum of a single particle, where the position is given by this relative position vector r and the reduced mass mu. Now in this case, because we have no external torque, the angular momentum here must be conserved, right? It's an isolated system. And in fact, we're going to take it to be magnitude L and along the z direction. So it's Lz hat. So that means, since it's a cross product of r and r hat, that means that both vector r and the velocity r dot, they are in the xy plane. So now what we've done is that we've actually reduced what was a three-dimensional problem up here to a two-dimensional problem. Essentially, there's no motion in the z direction, because both the position vector and the velocity vector have to be in the xy plane, the way we define things. So for that reason, we have a two-dimensional problem, and we can then rewrite the Lagrangian in polar coordinates. So that's our new Lagrangian. Now we can see here that it depends on r. It depends on phi. It does not depend on phi. It depends on r dot, and it depends on phi dot. Since it doesn't depend on phi, we say that phi is ignorable. And that means that the corresponding generalized momentum is constant. That is, the Lagrangian with respect, the derivative of the Lagrangian with respect to phi dot is a constant. If I take the derivative of this Lagrangian with respect to phi dot, I get mu r squared phi dot. That's a constant. And we actually know what it is. It's going to be the angular momentum. So I'm going to call this L, the magnitude of the angular momentum. Also, for substitution purposes, we're going to rewrite this in terms of phi dot. So just to be a little clearer, I'm going to write it right here. Okay. So this takes care of the motion in the phi direction. And again, because phi is ignorable, that just means that the angular momentum is conserved. But we still have to write down the Lagrange equation in the r direction. Okay, if we do that, we'll see that actually two of these terms depend on r. So we will get here and this becomes a full derivative, by the way, even though this is a partial one, because u only depends on one variable. And on this side we only get mu r double dot. So that's our equation of motion. We'll see later that this actually is what we call the centrifugal force. Now, you are probably told in intro mechanics that there is no such thing as a centrifugal force. There's only the centripetal force. That is true. This is not a true force. It's a fictitious force is what we call it, and it comes about on this side of the equation because we're essentially moving into a non-inertial reference frame. The next chapter in the book is going to be all about that, but there is actually room in physics for centrifugal forces as long as you keep in mind that they are not a normal force. But we'll talk more about that later. For now, we'll just keep it as a term here, and we'll call it FCF. Right. So this centrifugal force, FCF, is mu r phi dot squared. And I can now make the substitution here because I know what phi dot is equal to. And I can get everything in terms of r only. So that's what it has. That's its form. Now this is a force, or it's like a force. We can write it as the gradient of a potential, if you like. This is because this is a fictitious force. This will be a fictitious potential, but mathematically it will work just the same. So we can see that FCF equals minus ddr of L squared divided by 2 mu r squared. And I'm going to call this expression U of CF, the centrifugal potential. Okay, so now we can take this equation of motion and just plug this expression back in there. There's a minus sign here, of course. And this is the component of a gradient, right, in the r direction. So the r component in polar coordinates of the gradient is just d dr. And we're going to call this, the sum of u and u centrifugal, u effective. So first let me just underline this. This is the effective potential. And there's also 2 missing here. So the effective potential is, again, not a real potential in the sense that it doesn't correspond to a real force. This part does. This is the radial force. But there's also this part which really comes from the portion of the kinetic energy having to do with rotation around the center of mass. But because this part of the kinetic energy doesn't depend on any velocity terms, we can incorporate it effectively into the potential like this. And we can use this potential, we can treat it as if it is a real potential. And that's what we're going to do from now on. And the next video, we'll talk about some of the consequences of having this type of potential.